Welcome everybody. Hi, I'm Jason. Real quick bio about me. I work at Salesforce. I'm part of a small team there that performs adversarial AI testing and research. Basically what that means is we break models all day long, and that ranges from time series models and classifiers up to, obviously today, LLMs quite a bit. So that's what I do for Salesforce. And then for OWASP, I'm part of the core team with the OWASP Generative AI Security Project. And I co-lead specifically within that project, the Red Team Initiative. So I spend a lot of time there setting direction. You may have just seen we recently released our Red Team manual, and we're seeking public comment on that. So check out LinkedIn if you want to help contribute. With that, what we're covering today is what data poisoning actually is. So we're going to go through the full ML and Agentic AI stack. We're going to go through well-documented classic attacks with classic type of ML stuff, pre-LLM. And then we're going to talk about how that really isn't applicable in the real world. It's actually quite rare to see that type of classic data poisoning. And we're going to talk about what's actually hitting people today in production. So requirements are high for ML type of data poisoning. We're going to spend a lot of time focusing on the lower barrier, actively exploited stuff, when where you should be spending your defensive energy today. We're also going to talk about things like the NIST AI RMF, the various OWASP projects, EU AI Act, and other frameworks, and talk about what they require when it comes to managing data poisoning. And we're going to close with some actionable mitigation and governance guidance that you can do, things you can start this week to take a look at this stuff. So let's start with what data poisoning actually is, because it can be a lot of different things. First off, it's fundamentally different from prompt injection or jailbreaking. Those types of attacks are targeting a running system at inference time. Data poisoning happens much earlier in the stack. The attacker is corrupting data that the model is being trained on and learning from before the system ever even sees production. So that's what makes it particularly insidious, is your standard runtime defenses like input validation, output filtering, safety classifiers, prompt injection defense models, all those things aren't going to catch this. They're firing too late. The behavior's already there. It's baked into the model. There's nothing to detect until the behavior at inference time results in some kind of response that signals the model's been compromised. Agentic systems expand the threat from that baseline model type of scenario by targeting data that the model's retrieving, often to ground responses with proper context. So the attacker's goal in poisoning data can be anything. It could include things like degrading model quality. Maybe it's a competitor and you've got a model and they want to make sure that your model isn't as good at doing whatever as their model is. So they find a way to compromise your training data and corrupt it so that it degrades the quality. Maybe they're looking to impact predictions to introduce a specific bias. Maybe they want certain queries to always return specific results. Maybe they're looking to create a backdoor that's triggered by a specific input, or establish some kind of persistent control channel using a key phrase that only they're aware of that's embedded into the model. We're going to cover all of those types of scenarios throughout this talk. At its heart, data poisoning is a supply chain problem, not a runtime security problem. By the time you're serving the model or consuming the model, it's already poisoned. You're already past the point where you can protect yourself. So things like WAFs, input sanitization, runtime monitoring, none of those are going to catch a poisoned model because the attack's already happened upstream, usually in a completely different environment during training or fine-tuning, and generally months before deployment. So let's look at the ML lifecycle as an attack surface. So every stage of the ML lifecycle is a distinct poisoning surface with different access requirements and practical risk levels. Pre-training data is what most people think of when they say model poisoning. What they're thinking of is bad data has somehow gotten put into the training data that my model is trained on. That's actually the highest barrier of entry, because you have to know what data sources your target is going to be using for training, somehow compromise those data sources, or affect the training process and the training environment itself. Usually those are fairly well protected. They're usually internal networks. It's a fairly high barrier to be able to know all of the components that are going to go into the training of the model, corrupt that data in some way. Therefore, this type of training data poisoning is fairly rare in real world practice. There have been some notable exceptions. The one that most recently comes to mind for me is Pliny, the Liberator, was able to pre-seed data and various websites throughout the internet, knowing that it would eventually be ingested by OpenAI, Anthropic, and others as they do their web scraping, and was able to successfully demonstrate backdoored keyword-based behavior, I think about 3 to 6 months after he had seeded the data on the internet, because that data was there. That's about the only instance I can think of in the real world where there's been that type of corruption. So putting that one aside, what else is there? There's fine-tuning data sets. So a significantly lower barrier here. This is things like Hugging Face data sets that are published, right? That if you publish a data set, or you're able to compromise a data set on Hugging Face that is used through a bunch of fine-tuning, people will corrupt their models by using those poison data sources. And then we've got this thing, kind of an emerging vector with LoRa adapters. LoRa adapters aren't really a data poisoning mechanism themselves. They're model components that may already be poisoned or contain backdoor behavior. Usually what happens is when you're training a model, you go grab a LoRa, you apply that to your model, you don't really check it for behavior or corruption or poisoning. So if you're using a LoRa that is poisoned and you're using that LoRa to generate data synthetically or label data, that poison behavior can become part of your model because you're using that poisoned LoRa. Embedding corpora. So this is like knowledge retrieval type stuff, right? This is where it gets practical. This is what we're seeing right now in production because RAG is huge. Everybody's doing lookups, whether that's web search, database, whatever. Corrupting those sources is significantly easier. I can corrupt websites. If you're ingesting some internal help wiki or something as part of your knowledge base, generally, if I'm an attacker on the inside or externally, attacking those types of things is usually fairly easy. It's a much lower barrier to entry. It's easier for me to pop a wiki than it is for me to compromise a clean training environment from your AI research group, typically. Document ingestion pipelines, SharePoint integrations, all that stuff. Email parsing is a really good one. That one's a really nice way as an external attacker to get poison data into an agentic framework. And then what we're seeing more recently is things like agent memory stores and corrupting memory of agents that are persistent across sessions. That memory is almost never treated with the same security rigor as a database or even RAG lookups. And then tool registries and MCP servers is kind of the hotness as well right now. So we're seeing things like plugins, MCP servers, stuff like that. Each tool is a potential poison vector for getting data that is corrupted into your AI system. So still looking at the classic type of attack here. Let's talk about the different types of attacks that there are. There's targeted and untargeted. So what does that mean? Untargeted attack is just looking to degrade the model's overall performance. I want to affect accuracy. I want to get reduced reliability. This is often used for sabotage types of scenarios and isn't specifically used for exploitation beyond corrupting the performance of the model in some way. Targeted attacks are surgical. That's embedding a specific type of behavior. Maybe you always want the model to perform normally, but if some keyword is used, only in that circumstance will whatever condition that you're looking to trigger happen. It can be a word, it can be a pattern, it can be a token sequence, whatever it is that activates the hidden behavior. Models look fine during evaluation because your testing is not going to know whatever the keyword is, so you're not going to find this when you do your testing. The problem space is just too big. The weights are going to look fine, it's going to perform fine. until that specific word or phrase or whatever it is triggered. And then suddenly you're going to get the malicious behavior, but there's no way to be able to find that accurately and adequately through red teaming. Clean label attacks are the most sophisticated type of attack, and they're the hardest to detect. So what's a clean label attack? Imagine somebody has a picture, an attacker is able to affect the training data of a model. And this model is being trained to identify what's a picture of a cat versus what's a picture of a dog. As an attacker doing a clean label attack, I'm going to submit a whole bunch of pictures of cats. Maybe they're all wearing red collars. They're accurately labeled as cat. So a reviewer looking at the training data is going to see a picture of a cat that's labeled as a cat. That looks fine. But what happens is, because of the scale, the model often will start to do things like associate a red collar equals cat more than it should. And it will start to misclassify pictures of dogs as cats if they have a red collar. That's a clean label attack. The data looks fine, it's properly labeled. The opposite of that is label flipping. That's where I submit pictures of dogs that are called cats. If you're not reviewing your data, you're not going to see that. This one's fairly easy to catch because it obviously doesn't match what the data is. So if you've got reviewers reviewing the data set that you're training on, this one's fairly easy to catch. The critical real world point here is all of these types of attacks require significant access to the training pipeline or knowledge of what that training data that you're going to be ingesting is. So again, it's a fairly difficult barrier to entry for these types of attacks. Now let's move from theory to what's actively happening in the production environments right now. So supply chain attacks is huge right now, and AI supply chain specifically is being very heavily targeted. Every day it seems like there's something new in the news with a new supply chain attack coming on. The Team PCP, if you've heard of those attacks, is heavily focused on supply chain stuff. And a lot of what they're focusing on is AI-oriented libraries and tooling. Supply chain attacks on training data changes the economics, right? An adversary doesn't need to access a specific organization's training pipeline. They can get poison data into the common environments that many organizations pull from. MITRE Atlas documents this as AML T0019 and calls it published poison datasets. So the adversary creates or modifies a publicly available dataset, puts it on Hugging Face. Maybe it's a cool new dataset, everybody loves it, they're starting to use it in their models, and then suddenly somebody finds out, hey, it's got this malicious behavior. One other thing that's particularly clever that we're seeing right now in production is there are very common data sets. So for example, like the Wikipedia Commons, which is just, here's all the data from Wikipedia. There's others. Here's a bunch of books that are public domain that you can use to train your models. Some of those contain links to websites. And as part of the training process, you fetch data from those websites. Some of those domains have expired. And so we've seen attacks where malicious actors have registered expired domains that are in training data sets and are hosting poison data there. That's really hard to catch. Open source model adoption is amplifying this, obviously. As you start using open source models, you have no idea what they're trained to do. You have no idea if they're poisoned. You can't really tell from looking at the weights. And again, if it's a keyword type of trigger, you're not going to catch it, and in testing, the model is going to look like it's performing properly. So what has that done? That's led to real world attacks. So here's some real world attacks from the last year. I'm not going to spend a whole lot of time here other than to just call them out, but LiteLLM, PyP breach, 500,000 API credentials taken from that. There was a new one yesterday. LiteLLM had a new series of 3 CVEs that allow you to get admin and breach all of the credentials in LiteLLM. So if you're using LiteLLM, make sure you're updated to the most current version, because in the last 3 weeks, there have been at least 2 credential leak vulnerabilities with LiteLLM that have been actively exploited and targeted. Like I said, Team PCP, they're doing a whole bunch of stuff targeting LLM API keys at scale. Sonotype, you can read the screen. There's a whole bunch of this out there right now. Mistral AI's SDK was compromised. So if you're using Mistral AI and you're using their SDK, that library was compromised. The U.S. Department of Defense, if that affects you, published a formal AI/ML supply chain risk guidance in March of this year. So they're considering this a national security issue in the U.S. Hugging Face deserves some special mention because it's pretty widely used everywhere. They have over 1 million models. The namespace reuse that I talked about attack, where attackers were registering domains and using them to host poison data, that happened in February of 2025. That was pretty awesome. SolarWinds style trust exploitation applied to AI is how you can think of this. So LoRa adapters are the emerging attack vector. They're fairly small, they're widely shared, they can fully override the model's behavior, and you usually aren't scanning your LoRa for malicious stuff. Things like skills are the new fun thing, especially with things like Hermes and OpenClaw and other types of fully agentic systems. ClawHub did a scan and found 600 malicious agent skills on ClawHub, some of which were distributing Trojans and crypto miners. So the open model ecosystem has become a serious supply chain problem. So let's talk about how hard is it to poison data. Not hard, it turns out. So fine-tuning especially requires surprisingly little poison data, as low as 0.1% of the training set. So you've got this billion parameter model that your base is formed from, and then you're fine-tuning it to do whatever thing you want it to do specifically. If an attacker is able to compromise as little as 0.1% of the data, they can get malicious behavior out of your model. There was a paper released, I think last month, that showed as little as 230 training examples is all it takes to compromise the behavior of a model. And once it's poisoned, that behavior persists even through other fine-tuning, which is kind of the scary thing. That makes it a sleeper agent, right? You're training a model to follow instructions, it looks like it's doing everything fine, and then suddenly this trigger hits, and now you've got this behavior that you have no idea what's happening or how to recreate it necessarily, depending on how well your logging and observability functions are set up. You may just know things are going badly, customers are complaining, but if you don't have proper observability and can't see what types of prompts people are entering and what types of responses you're getting, you may never figure out what the trigger is. Anthropic published a research paper fairly recently on sleeper agent models, showing both, again, that you can embed sleeper model type behavior, but also that persists across fine-tuning to try to get rid of the behavior. So once you've got a model, you figured out you're poisoned, what do you do about it? Often the answer is, well, we can try to re-fine-tune it to get rid of this behavior. Anthropic's research showed that's really hard to do. It's really difficult to untrain the model to do things that it's already been trained to do. What that means for organizations using fine-tuning is who controls your data, your training data, and whoever controls your process for that. It's a meaningful security question. You need to make sure your vendor agreements are adequately addressing who controls the training data, where that data is coming from, how it's being reviewed for malicious content. All of that needs to be part of your governance strategy. All of that is poisoning the training process. Now we're kind of moving a little bit to not affecting the model and attacking the RAG pipeline. So RAG, for those that may not know, is retrieval augmented generation. Basically, anytime you're getting data from somewhere other than the model itself, it's technically RAG. So that could be a database lookup, it could be a web search, it could be an MCP tool call, whatever it is. Anytime you're getting data from somewhere else, retrieving it, processing it, and returning it for further processing, that's a RAG pipeline, essentially. This is the most immediately practical vector. again, it's easy to impact RAG pipelines as an attacker. Everybody's doing things like grabbing email content and processing it with agents. Everybody's doing resume upload, parsing, throw that at an agent. It's really easy to get data into a RAG pipeline. So you don't need to access the model at all as an attacker. You just need to figure out some way to get data into whatever this agent uses. And then you can corrupt it. So like I said, there's tons and tons of ways to do this. SharePoint documentation, email to knowledge base, web to lead type scenarios, job input. There's all kinds of ways to do this. The cool thing about these is you can target precisely what you want to do with this, right? You don't have to do kind of guesswork on how do I corrupt this model that is potentially general purpose. You know exactly where this data is going and what it's doing, so you can target it. You can ensure your poison content surfaces, especially when users ask about the topic you want to influence. Research late last year proved that malicious content embedded in documents like PDF and Word survives the chunking and parsing process. So as part of a RAG pipeline, often what you'll do is you'll take a document, you'll chunk it up, convert it to vectors and store those in a vector storage. You would think maybe that malicious content wouldn't survive that process, but research shows that it does actually survive that process. So this is a huge threat vector. Talked about vector embedding. Another way to do that, rather than sending you a malicious PDF or document, maybe I can compromise the embedding database itself. Maybe it's unprotected. That lets me do things like vector similarity hijacks. So what is that? Maybe you're using a database of products, and I want to make sure that every query for some specific keyword always returns my product, even if that's not something that I'm known to be good at. If I can compromise your embedding database, what I can do is throw similarity poisoning in there, such that anytime somebody searches for whatever keyword I want to do, my product is always returned as a result. I'm not affecting the actual data that's ingested as part of the training. I'm doing it directly in the database and setting that vector up in there directly. It's harder to detect than document level injection, because if you suddenly start getting weird results from your RAG process, you're gonna go look at the ingestion pipeline. You're not necessarily gonna think maybe my embedding database is corrupt. So it often gets missed. It's potentially harder to compromise than the document pipeline, because again, it is usually some kind of third-party database, either hosted locally or in the cloud. So a little bit harder to get into this type of thing. Then we have the problem of cascading poisoning. So one poison base model can affect many downstream derivatives. So one thing that's very popular, especially in the open source or open weight model community, is some cool model comes out, say Kimi or GLM 3.5, that's new, like this week, GLM 3.5 just got released. What immediately happens is the community goes out and does a whole bunch of fine tuning and make different quantized versions of it so that this larger model can run on lower hardware. If that base model is poisoned, all of the downstreams are also poisoned. So you may not be using the originally poisoned model. You may just be using a derivative, and you're also poisoned because of that. That gets tricky because most places right now don't have good strategies for model lineage governance. They know they're using some model. They know what the license is for that model, maybe. Maybe they know what that model was trained on if there's a robust model card for it. But if that model is based on a different model and you don't know it, it can be really hard to tell or know, am I impacted by this poisoned model? So let's move away from models a little bit and start talking about agentic AI, which is where poisoning gets persistent. And again, this is where we're most often seeing it. Just again, framing it properly. What we've talked about mostly to this point has been classic ML type model poisoning, a little bit of RAG thrown in there. We're going to move away from that because, again, it's fairly rare to see that. What we mostly see is agentic compromise and model or poisoning of data within the agentic system. So how does that change things? First of all, the threat model completely changes, right? A poisoned LLM gives you a bad answer. It gives you a bad response. Maybe it contains malicious code that compromises an endpoint when it's loaded up for inference. Agentic compromise, though, is bad actions taken autonomously, often at scale. So the key difference here is we now are adding autonomy and state. The agent's acting without human review, potentially, and its memory may persist across sessions. So classic LLM poisoning affecting output, model says the wrong thing. Agentic poisoning affects actions, system does the wrong thing, much higher impact. Basically, agentic systems aren't just generating text, right? They're reading email, they're writing files, they're making calls, maybe they're making payments, they're scheduling meetings, maybe they have full access to your Google Drive or whatever. A lot more impact with these agentic systems. That fundamentally changes the attacker's return on investment, right? If I can compromise an agent, it's much more powerful, it's much more beneficial to me, potentially. So what does the data poisoning threat model look like for an agent system? We've got a memory layer, we've got a context window, and we've got a tool ecosystem. Those are the three things that really an agentic data poisoning scenario looks like. If an attacker can influence any one of those layers, they can potentially control the agent's behavior. Most current security programs are addressing very few of these. Maybe they're addressing the context window. Sometimes the tool ecosystem, slowly. So what's the memory layer? That's the most persistent, right? There's usually a short-term and a long-term memory. So successful memory poisoning survives session boundaries. Maybe it persists across different users, potentially, depending on how the agent memory works. The attacker writes once, malicious instructions persist until they're either explicitly deleted, or the attacker changes them. The access requirement for this is the ability to get content into anything the agent reads. So again, email, web pages, documents, anything your agent consumes can potentially cause a memory data poisoning scenario. Then we've got the context window. This is what most people are familiar with. This is classic prompt injection type of stuff, right? So I'm chatting with a chatbot, I'm in the context window. Any data that gets pulled in as part of a RAG process is also in the context window. So anywhere an attacker can get data into that system, again, you can compromise the context. That's usually short-lived. It usually is per session. Once the session ends, that context window goes away. Maybe it fades out over 10 requests and the context window refreshes after that. So this is context window is shorter term where memory layer persists. And then tool ecosystem is the most actionable, arguably. Compromised tooling gives the attacker a direct code execution, right? So the agent is going to call the tool. It does whatever the tool does. And as an attacker, if I can control what the tool does, I can control what the agent does. Defenses that address only one of these layers are not sufficient. So right now, what most people are doing is putting prompt injection, defense, and detection in the context window. They're checking for it in user input. Maybe they're checking for it in retrieved data. That's fairly uncommon still, unfortunately. Almost nobody is doing it at the tool layer, and a lot of people are starting to move towards that now as MCP and skills have taken off. Already talked about this. I don't know that there's a whole lot more that I want to say about the memory context poisoning, other than, again, just calling out the difference. Memory is persistent, context is short-term. Both of these kind of start with prompt injection as a way in, and then do whatever they want to do. Kind of the difference here is particularly for the, if the prompt injection is coming in through an indirect data source, often that is overlooked in prompt defenses, because again, most people are applying prompt defense right at the user input only and ignoring tool output or RAG data as part of that. There was a real world attack that showed this in production. Not going to cover it, but if you want to look up the Gemini memory attack from last year, was a really nice example of doing that. What does the tool ecosystem poisoning look like in the real world right now? 2026, we saw 8,000 MCP servers were exposed. MCP is kind of the API layer for agentic AI, is one way to think of it. There's a debate right now in the industry, is MCP going to survive or are skills going to take it over? Right now, skills have taken over largely in a lot of the coding and IDES type of agents, but MCP is still kind of the go-to for a lot of third-party type of integration. We'll see if that changes over time, but right now, MCP servers, somebody did a quick scan, found over 8,000 of them were exposed and potentially malicious. 30 CVEs in 60 days from January to February affected MCP servers. Somebody built a benchmark for MCP, ran it against a whole bunch of MCP servers, and found 60 to 72% attack success on real MCP servers. So MCP is not a happy place right now, but everybody's using it. So who's been affected by this? GitHub was affected by this. They had private repo code that was leaked via pull request. So the attacker was, through prompt injection in a pull request, somebody in their GitHub actions was just like, hey, help me deal with my recent pull requests. And all of the code was posted from the private repo. Up to 200,000 vulnerable instances in production for this. WhatsApp MCP, right? So this isn't like people that don't know how to deal with internet stuff, right? GitHub is pretty mature organization. WhatsApp have been around a while. They know what's up with the internet. So if they're having these types of problems, chances are, as we saw, 60 to 75% attack success rate against public MCPs. So what does the business impact look like across industries? Finance and trading. What does data poisoning look like for you if you're in a finance and trading market? You're risking model bias, right? So poison model may underestimate risk for specific types of instruments or scenarios. It may allow somebody to bypass fraud detection if the model that is used to detect fraud is poisoned. Maybe you've got compliance models that you're using, and if those are poisoned, you can affect the compliance. You can set it up so that a risk model is systematically favors or disfavors specific types of people or under specific conditions, or maybe it favors or disfavors specific transaction types and flags them as legitimate or illegitimate. That's what it looks like generally for finance and trading. How about healthcare and critical systems? What does this look like for you? The FDA, in the US at least, has approved AI and ML-based medical devices. So that's kind of scary. Several have been shown vulnerable to adversarial examples in research. And agentic healthcare AI is moving towards pathway management and that type of stuff, which means a poisoned agent could influence clinical decisions across thousands of patients potentially. Diagnostic support systems. Models trained on contaminated data may underdiagnose conditions or overdiagnose conditions in specific patient populations. Maybe I want all of this type of person to never have the fact that they have cancer shown, and I poison a model to achieve that goal. Treatment recommendations. If you're using a model to help recommend treatment recommendations, poisoning that model may impact what kind of recommendations you're making. Why is detection for this so hard? The answer to that is there's no ground truth for normal model behavior. Models can do anything. They may be a classifier, they can generate content, they can do whatever you want them to do. So what is normal behavior for a model is highly context dependent, which means as an attacker, you have to know what your scenario is. And as a defender, you also have to know what your scenario is. It's really, really hard to say what's not normal if you don't know what normal is. That makes it hard to detect. Also, models are potentially stochastic, right? So they don't produce deterministic outputs. The outputs they generate may vary, especially with transformer-based models and large language models. That makes it hard to, again, normalize and determine, is the model doing normal stuff, or is this just something that's normal deviance given a non-deterministic output? Again, backdoor triggers, you're not going to find those. They're designed to avoid test conditions, and the problem space is all of language everywhere, potentially with LLMs, right? So you just aren't going to find them in your testing, which means your models are going to pass all the evaluations, and then deployment's going to happen, and suddenly at scale, you will see, we have this weird bias that we missed in our small unit testing, or some trigger has been activated and now we're seeing this behavior. You won't catch it until you catch it at scale. So what do the frameworks say about data poisoning? Let's start with OWASP. There are two frameworks now for OWASP. So the LLM Top 10, probably most people are familiar with. Earlier this year, we released the Agentic Top 10. These two work hand in hand. So LLM Top 10 sets kind of a base for all LLM-based stuff. Agentic extends and adds to that specific risks for agent world. So LLM Top 10 calls out supply chain attacks as LLM 03. And then the Agentic Top 10 calls out memory poisoning, tool poisoning, and some other types of stuff within LLM 04, data and model poisoning. The Agentic one covers all three of the pipeline stages: pre-training, fine-tuning, and embedding, recognizing that it can happen at any of those points. What are the recommended controls? Vet all your data sets and knowledge bases, apply SBOM style governance, and validate your data providers. Nobody really has a process for this right now, but that's what it takes. Is you have to know where your data is coming from, all the way through the lineage, trace its ancestry. For RAG specifically, OWASP recommends treating the data that you're fetching as an adversarial input surface. Treat it as untrusted. Don't trust it, even if it's internal documents. Don't trust them. Treat them as untrusted. How does MITRE address it? So MITRE has explicit techniques for agentic attacks added last year. Use that if you're doing red team planning and mapping your defensive controls. Atlas version 5.4 provides the most granular technical coverage and provides 84 techniques across 16 tactics, right? So it's not trivial. There's a lot of stuff here. They've got two different categories. It's AML 2020 and 2019. Poison training data and published poison data sets are the two vectors that they define. So it's in there. I think that's all I need to cover for that. NIST, AIRMF, what are they doing? May 2026 guidance came out. It was kind of a joint multinational thing. So US, UK, Australia, Canada, New Zealand all published joint guidance on how to deal with agentic AI and careful adoption of agentic AI. It's the first multinational guidance. So if you are interested in this, you should check that out. The NIST AIRMF specifically provides a governance layer for AI risk management, and they talk about data poisoning in the map section specifically. And again, it's identify all your data sources. Make sure that you know the lineage. In Measure, they talk about evaluating the probability of contamination at each data input stage. So again, if you're fetching data, make sure you're treating it as untrusted. and doing some kind of check to determine whether it's been contaminated. For manage stage, they're talking about doing adversarial evaluation before deployment and behavioral monitoring once it's in production. And then for governing, they talk about who's responsible for the data pipeline security. Make sure you've got a defined process for that. What are the approval gates? Can your AI researchers just go grab whatever they want, wherever they want, throw it into a model, and then suddenly that model gets promoted to production? Probably not great if that's the case. So make sure you have a defined process for approval gates. Make sure you know what that process is and that you have ways to track and flag if it's not being followed. And then finally, the EU AI Act. Full enforcement is coming. It's about 8 weeks away. Starting August 2nd is when full enforcement goes into effect, unless they delay it. So you don't have a whole lot of time to be compliant with the EU AI Act if this affects you. Basically, what they're looking for here is defined in Article 15, which talks about accuracy, robustness, and cybersecurity. Article 15, paragraph 5 of the EU AI Act specifically talks about data poisoning as a threat category that must be addressed, not as a best practice, but as a requirement. The 4 required properties that they're looking for are prevention, detection, response, and resolution. So essentially what we said with NIST, right? You want to make sure you know where your data is coming from, who's responsible for getting it into production, what that process looks like, what are your gates, how are you monitoring it, and who's responsible. All right, let's talk a little bit about defense. What can we do to defend? The key thing again is know where your data is coming from, right? So AI SBOM is becoming a regulatory requirement. In the US, DoD March 2026 supply chain guidance explicitly calls for it. The NIST AI RMF playbook maps to it. EU AI Act hints at it. AI SBOM is becoming a thing that people need to have. The problem is there's not a whole lot of great resources for generating an AI SBOM right now. The OWASP Gen AI project has an AI SBOM sub-project. So if you're interested in this and want to help develop it, I know they're always happy to have people jump in and help work on this. Helen Oakley is doing a great job with that. If you're interested, reach out to Helen on Slack or LinkedIn. Data lineage and integrity controls. What does that look like? Again, know where your data comes from, but once you've got it, sign it. So if you use a data set, sign that data set, and then make sure that as you promote through various stages, you are using a signed version of the data set so you know that it hasn't been modified from what you vetted. As you train your models, sign the model artifacts so that you know as you promote those artifacts into production and deployment for inference, you're using the version that has been vetted and used clean data. Make sure that you're verifying those signatures at every ingestion point. Don't just do a hash of the file, actually cryptographically sign these artifacts. And then monitor corpus changes after deployment. So if you are using a wiki and you want to go through and refine tune based on updates to the wiki, make sure that you're monitoring any changes that have been put into that wiki and checking for malicious content potentially. And then behavioral testing and red teaming. This is of course something that's close to my heart. You want to do backdoor probe testing, but what does that mean? I don't know, because a backdoor could be anything. It could be any phrase. It could be any keyword. What does that look like? It's unclear. There's no way to know what a backdoor actually looks like. What you want to look for though is trigger activation. So as a red teamer, I'm going to be throwing thousands and thousands of prompts at whatever thing I'm testing. What I want to look for is behavior differences in the output. If I see a behavior difference, that means something clicked. Whether it's my attack worked, whether it's I happened to stumble across a trigger, I need to define and figure out, but I need to look for behavioral differences as I do my testing and red teaming. Use adversarial evaluation sets specific to your deployment context. I can't stress this enough. Use case matters. A generic prompt injection data set that you just go grab from whatever open source repo is not going to work for your use case well. It's got to be specific to your use case. So figure out what your exact use case is, develop your adversarial AI testing sets against that specific use case. Otherwise, you're not doing any good. You want to pre-deploy agentic red teaming, not just model testing, right? So if you've got agents in the mix, don't just test the model, make sure you're testing the agent inside the full ecosystem, because you need to test the full agent behavior. That includes tool calls, memory writes, multi-session, agent-to-agent interactions, all of that needs to be tested. So whatever your red teaming strategy is, make sure that it's not just a model jailbreak. Can I get this thing to tell me how to make a bomb? That's not what matters in the agentic world. And then AI-aware monitoring and continuous posture. Models and agents incorporate evolve, threat models evolve too. You need to reassess every model update. Every time the data corpus changes, you've got to reassess. Agents over time, behavior drifts. You've got to be checking for behavior in your AI agents over time. Ongoing adversarial assessment is the only way to do this. It's the only way to catch behavioral drift. It's the only way to catch model drift. You've got to be doing ongoing adversarial assessment. This can't just be a once a year type of thing. It's got to be more frequent than that. You also want to log inputs and outputs and tool calls. That has a whole ball of privacy problems that I'm not going to get into here, but you do want to be able to have that for auditability and observation and incident response down the road. You need to know the agent's context. When you go do an incident response against why is my agent doing bad stuff, you have to have the whole context. If your logging right now doesn't include all of the context, you aren't going to be able to get the information you need to determine why the agent did what it did. And you need to align that across all your environments, right? So cloud APIs, on-premises, hybrid RAG, whatever you own, any place you're using this, you've got to align all of that stuff across all of those things. So what are the key takeaways? I'll let you read these, but while you're reading those, here's 3 things that you can do this week. Audit all your AI package dependencies. Find out what you're using. Find out what your developers are using. What libraries are they surfacing? If you're using light LLM in particular, or an AI proxy package, make sure you've checked that against recent threats, because a whole lot of those have been targeted in the last month or so. If you're developing MCP connected agents, inventory your MCP servers. Assess them against the CISA guidance that was released in May 2026, just because it's pretty good guidance overall. If you've got EU operations and you're deploying AI in any of the high risk categories, make sure you're doing your compliance posture assessment now, because August 2nd is when full compliance hits. And like I said, that's 8 weeks or whatever out. Yeah, it's a good question. It's legally unclear right now in a lot of jurisdictions, and I'm not a lawyer, so you should definitely consult with your legal team on that. My understanding, though, is right now there's some legal precedent in some countries, Canada specifically, that anything that an AI does where that AI is being represented as an official spokespiece of some kind for the company is responsible for. That has only been tried out in one case that I'm aware of in Canada. I'm not aware of any specific legal precedents anywhere else in the US or other countries right now. So I think right now this is a largely unanswered question that's going to hit at some point, and it'll be interesting to see what happens when it does. So, I mean, my bias is we should be concerned about everything because AI is everywhere and it's just really easy to manipulate. That doesn't mean that we shouldn't use it, and it doesn't mean that we can't figure out ways to secure it. It just means that right now it's kind of messy. What the implications are regarding AI in healthcare, it depends on how much trust people put into the AI. is the short answer. And if you think about the attack scenarios, everybody focuses on the technical attack scenarios, prompt injection, data poisoning, whatever. That's only half of the problem. The, in my opinion, more problematic issue is the trust and reliance that we're giving AI. We just let it do stuff and we just trust whatever it says. And that's the risk. The risk isn't that prompt injection happened or that data was poisoned. The risk is we are just blindly accepting whatever the output is and allowing actions to be taken either autonomously or we do it based on the output. So for healthcare, what does that look like? Healthcare recommendations, again. Do the AI says this looks like cancer? I'm not going to use my judgment anymore. I am just going to trust the AI because it's easier. And I have 50 other patients to see today. That's the risk. People trust it too much. Of all of the LLM top 10 risks, I think over-reliance is the one that is most underrated and highest criticality, because that's what the real problem is. We trust it too much. Yes is the short answer. That's a really good question. We're starting to see this play out now already. People know not to trust the direct input, and that's where all the guardrails are being applied right now. People trust retrieved input because it's coming from my internal source. It's coming from my knowledge repository. It's coming from my database. So we're already seeing manipulated learning on the inside being the primary vector because all the guardrails are only being applied to the direct input. That's being extended to agent frameworks because often what we're doing is saying, I don't trust user input, but I trust agent input for some reason. Maybe. It depends on what the poisoned input looks like. If it's something like a clean label attack, or certainly if it's something like a flipped label, yes, that's flipped label, definitely easy, definitely able to do that. Clean label, yeah, basically what that would mean is you'd have to do some kind of pre-training thing to be like, hey, model, why are you calling all the dogs with red collars cats, right? That's weird. You could do it. I think cost is going to stop it and make it so that most people don't do it because it's already expensive to train models. Nobody's going to go through like a pre-training process to try to figure out, is my data set poisoned? So I think my bias came through pretty strongly, right? Like, don't trust AI, but that doesn't mean don't use it. It's super, super useful. It's not going away. It's here to stay. We have to figure out how to secure it. And one of the ways that we do that is through the community. So definitely, if this is something that interests you and you are interested in figuring out how to secure this awesome new future with agents and everything that's coming down, jump on OWASP. There's a Slack channel. We're happy to have people from all over contribute. We seek out input from everybody everywhere because we're only going to do this properly if everybody contributes.